Hello students, welcome back to chemistry class brought to you by ighota virtual learning platform. I am Olabisi Olawoye. Today we will be considering a very important topic, and that is characteristics and nature of solid. This topic has been carefully selected from YX syllabus, and at the end of this class some Y questions will be treated that align with the topic taught in this video. And at the end of this class, as students, you should be able to classify solids into different forms and differentiate between the forms of solid, and we should be able to classify some solids into subgroups and then give examples in each case. Now, we all know that matter comprises of particles. Matter is any substance which matter is any substance which has mass and occupy space. And in the first video, the nature of liquids has been treated. It is generally known that liquids contains particles which particles which are held by weak bond, unlike solids. So in this section, we're considering solids, and solids have definite shape. They have particles that are well arranged. They cannot be compressed. They have high melting and high boiling point. So what are the different types of solids in chemistry? We have two types, which are crystalline solids and amorphous solids. And these they are classified or arranged based on their constituent particles. Now, crystalline solids generally have a regular repeated structure, unlike amorphous solids that lacks a kind of regular arrangement in their particles. Now, within crystalline solids, further distinctions are made based on the type of bonding and the constituent particles that leads to four groups of crystalline solids. The first one is the ionic solid. The second one is the metallic solid. The third, covalent network, and the fourth, molecular solids. So in this section, we'll be looking at these four groups of solids with examples, how they are formed, and their constituent particles, that is, particles they contain, and the kind of bonding that takes place in each of them. The first one is ionic bonding. In ionic bonding, ionic solids are formed as a result of ionic bonding. In chemistry, ionic bonding or ionic chemical combinations is also known as electrovalent chemical combinations. So how does electrovalent chemical combination occur? When an element gives out its electron, in the case of sodium for instance, it has one valence electron. When it gives out its valence electron, we will realize that sodium will become positively charged after giving out its valence electron. Valence electron is the electron at the outermost shell. So if sodium that has atomic number of 11 contains 11 electrons, and the first shell takes 2, the second 8, the third 1, which is the last shell, and is in need of 7 more, but very difficult to gain 7, it ends up losing the 1. And when elements loses, they become positively charged. The next element here is chlorine, for example, and these two combine together to form sodium chloride, which is a common table salt that we all use. Now, chlorine has atomic number of 17, meaning it contains 17 electrons, and when arranged, we have 2 on the first shell, 8 on the second shell, 7 on the last shell. This is a need of more, which gain easily from sodium. So when elements gains, they become negatively charged, and so sodium chloride reacts together to form sodium ion and chloride ion. So in this case, ions are formed as a result of losing or gaining electrons to become positively and negatively charged respectively. And whenever there's an opposite charge, electrostatic attraction occur or arises, which leads to crystalline ionic solid. So ionic solid is very strong. The solids are very, very strong, and the ionic bonding too, which is also electrovalent bonding, is very, very strong. The next one is compared to covalent bonding. The next one is metallic bonding, which consists of metal atoms held together by a sea of delocalized electrons. So metallic solids are formed as a result of metallic bonding, and in this case, this bonding occurs between electropositive elements, which are metals generally, that is, elements with one or two or three valence electrons in their structure. Because of their free valence electron, they become negatively charged. Because of the free valence electron, the electrons are negative, so to say, which are found on the shells, and then the elements themselves are positively charged because they have the tendency of losing electrons. So a kind of attraction occurs between the positively charged ions and the negatively charged electrons, which forms a kind of metallic bonding, and that is responsible for the hardness of metals. So, and metallic bonding is formed as a result of delocalized electrons. And the higher the valence electrons of a metal, the stronger the metallic bonding in that metal. For instance, aluminum has 3 valence electron at the outermost shell, while sodium has 1. So metallic bonding in aluminum is stronger than that of sodium. The next one is covalent network bonding. Solids, which are formed as a result of covalent bonding. Now, these have a network structure of atoms linked by covalent bonding. A very good example is in diamond. Diamond is a form of carbon. There's a crystalline form of carbon, where a carbon atom is bonded to 4 other carbon atom in a tetrahedral arrangement, which is very strong. So carbon reacting with carbon is covalent bonding, and in this case there's sharing of electrons between the atoms to form a kind of a well-arranged pattern. Another example is graphite and silicon dioxide. So all these these are all examples of covalent network solids. The next one is molecular solids, which are formed by molecules held together by relatively weak intermolecular forces like van der Waals forces and hydrogen force. Why do we call it intermolecular? That is, the forces arises between molecules of water, for instance, and between water and another water. Now, unlike within hydrogen and oxygen of water itself, that is covalent bonding, but between water, that is oxygen, and another hydrogen of another water molecule, that is hydrogen bonding, which is very weak. So when all this happen, you know, we have aggregate of a lot of water molecule in a bowl of water. It results into aggregate of hydrogen bonding, which accounts for the strength. And so that's why a solid is being formed like ice in that case. And it is found that in molecular solids, they are weak and they sublime easily. A very good example is in iodine too. Iodine sublimes easily when heated. Between iodine and another iodine, we have a kind of van der Waals forces holding them together. So van der Waals or hydrogen force is their weak forces that holds molecules together, and these molecules end up forming solids, which can sublime easily or melt easily. Another example is in naphthalene. Naphthalene also sublimes easily when heated. So this is because that sublimation in this case is changing from gases directly to changing from solids directly to gases without passing through the liquid phase when heated. So this is a result of weak bonding holding the particles together, and so molecular solids arises in this case. So having described the 4 classifications of solids, we have the amorphous solids too. Amorphous solids does not really have a regular pattern, just like as described earlier. The solids are formed as a result of weak bonding, and they don't really have a kind of bonding. An example is glass, rubber, plastic. They melt easily and they do not have a well-arranged regular pattern. So how are particles, ions, atoms, and molecules? How are they arranged in solids? In solid state, particles like atoms, molecules, or ions can be arranged in either a highly ordered repeated pattern in the case of crystalline solids, or a more random disordered arrangement in the case of amorphous solids. A very good example in this amorphous has been mentioned earlier, like glass, rubber, and some plastic. As we can see in this diagram, we can see the particles of solids in crystalline solids well arranged. So this form the basis on which their properties arises, and so we can see a kind of repeated pattern, and it gives solids a kind of rigid or definite shape. And this can also arise into a lot of things like high melting or boiling point, high melting point, so to say, that is high temperature required to melt a solid. Unlike the arrangement of amorphous particles, these arrangements are not in a regular form. So from there we have the first one here, which is the crystalline solid. Let's quickly consider different crystalline solids and how their particles are arranged. What kind of particles arises in them and how are they arranged? Crystalline solids particles are arranged in a repeating three-dimensional pattern, which results into what we call crystal lattice. A very good example is in covalent ionic solids. The ions of sodium and chlorine in ionic solids end up forming a kind of crystal lattice as a result of the electrostatic attraction between the positive and the negative ions of sodium chloride. This ordered arrangement gives crystalline solids a definite shape and can be observed at a macroscopic level. That is, they can be seen easily. Now, a very good illustration is using this kind of pink and purple arrangement where the particles are well arranged following a kind of pattern. We can see positive a purple being arranged on the pink form, and in a case where the same colors are facing each other, there will be a kind of repulsion. So in ionic solids, electrostatic attraction occur, and that leads to the crystalline form. Another example is in metallic bonding. Metallic solids have a kind of regular structure where metals are packed in a sea of delocalized electrons. So there is a kind of attraction between the positive ions of the metal itself and the free valence electrons arising as a result of this metal. So the electrons are negative, and we can see the structure. It forms a kind of rigid structure, and this is responsible for the hardness of metals. So in a nutshell, crystalline solids have a well-arranged particles forming a kind of crystal. So the next one is network solids, which is covalent network solids. These are formed by covalently bonded atoms, and the atoms are arranged in a three-dimensional structure or network. And networking is a bit hard to break down. When there's a network, you see that the particles formed there will be very strong. Examples include diamond and quartz, which contains silicon and oxygen. In diamond, we have majorly graphite is another example. Graphite also contains majorly carbon. Diamond contains carbon. That of carbon is made, I think I've described this earlier, where I described that diamond is made up of carbon to carbon bonding, which are covalently bounded together. One carbon is covalently bonded with 5 other carbon atoms, resulting into a kind of network. And one of the reasons why diamond is hard is because of the covalent bonding. Though covalent bonding is not as strong as ionic bonding. But when there is a network, this form a kind of tetrahedral shape, a three-dimensional network, and in this case a kind of crystal is being formed, and that's one of the reasons why diamond is the hardest substance known, because it's very, very strong. The carbon to carbon bonding in diamond is well arranged in a tetrahedral shape, resulting into the crystal of. If another example is in graphite. In graphite, carbon reacts with another carbon to form a kind of crystal. So both of them are the forms of crystalline solids of carbon. So the third example of network solids, like covalent network solids, which also accounts for reason why they are strong. The third type is a quartz, which is made up of silicon and oxygen. How are the atoms arranged here? They are also arranged in such a way that a network shape is being formed between the silicon and the oxygen. There's a kind of network arrangement being formed, and this arrangement results into a kind of crystal lattice. So from here we can see that most crystalline solids arises as a result of a kind of bonding in which the particles are well arranged in a regular pattern. And that of graphite and diamond, that one is arranged to form an octahedral shape. The other one is arranged to form a tetrahedral shape. And this is as a result of the covalent network solids in the bonding. Unlike amorphous, we also have amorphous form of carbon. I'm illustrating more on carbon here because carbon is a non-metal, but it has two substances that are under it, like the crystalline solids and the amorphous solids. So the amorphous form of carbon, they are in form of soot, like charcoal in form of soot, that's powdered form. Anything amorphous is very, very soft and not regular, while the crystalline form of carbon is the graphite and diamond. And out of these two, diamond is the hardest substance known. And what is responsible for this? Because of a well arranged covalent bonding between a carbon atoms. Unlike graphite is not as strong as carbon because they are arranged. It's also made up of carbon to carbon atom, but this is arranged in such a way that not all the carbon bonds together with the neighboring carbon, and that is why it is not as strong, though this will be treated later in the next video. And because graphite has some special characteristics and interesting characteristics, and that brings us to the end of the class. So under here we'll be treating some revision questions, and I want you to go through these questions now. We'll pause the video, go through the question, try to solve it based on what we've done, and then come back, we'll solve them together. So here now, the first question: strength of metallic bonds depends on A, the charge density of the atoms, B, the ductility of the metal, C, the number of valence electrons. This is year 2019 WAEC. The best answer is option C. Please, anytime you're answering a question, always go through the options properly before arriving at your answer. I told you earlier that the strength of a metallic bond depends on the number of valence electrons. In the case of aluminium has 3 valence electrons, while sodium has 1. So aluminium has more a strong metallic bonding. The next question: particles in solid exhibit A, vibrational motion, B, vibrational and translational motion, C, vibration and random motion, D, random and translational motion. The particles of solids can only vibrate, they cannot translate or or move about. They can't move about or so in this case they don't have enough energy to translate because the particles are held by strong bonds rigid in a position. That accounts for the reason why they have a definite shape. So the best answer is in option A. Now third question is solid with high melting and boiling point is likely to be, is it a covalent compound, a dative compound, an electrovalent compound, and a non-metal? Generally considering covalent compound, except in the cases of graphite and diamond especially, those are exceptional cases. In generally, the compounds of electrovalent bonding, which is also ionic bonding, is stronger than that of covalent bonding because ions are formed which arises into what them having high melting and boiling point. So the best answer is option C. The next question, consider each of the following substances: sodium hydride, hydrogen sulfide, ammonium chloride. Describe the nature of the intermolecular forces holding the units or molecules together in the condensed form. More of these intermolecular and intramolecular forces will be treated in the next video. But here now we have sodium and hydrogen. Between sodium, which is positively charged, and hydrogen, which is also generally known to be positively charged, we can see here that there's a kind of attraction which is electrostatic anyway, because there's a potential difference arising between the positive and the partially positive hydrogen, which results into electrostatic attraction. So it is ionic in this case. But they can also, sodium cannot share with hydrogen, so sodium transfer directly to hydrogen, which has a tendency to gain more compared to other positive elements. The next one is between hydrogen and another hydrogen, which is covalent sharing takes place here. And between hydrogen and sulfur in hydrogen sulfur, there's also a kind of sharing between them, between hydrogen and sulfur. They share, none of them is ready to give out, unlike sodium hydride. And the last one is ammonium chloride. Between nitrogen and nitrogen itself, we have covalent bonding between nitrogen and 3 hydrogen in form of covalent sharing. But between ammonia and NH3 and hydrogen ion, we have dative bonding. And then between the ions form, positive and negative chloride, we have electrostatic attraction, which is ionic in nature. And this ends brings us to the end of the class. I must commend your effort to paying attention to the end. I want you to treat more questions under this section and then watch out for the next video, which is